this is our experimental apparatus right here. You can see a zoomed in view in this section, and it consists of a tungsten needle right there that is surrounded by this sheath. This is a cross section of it, so this actually is like a sheath that goes around this needle. And that turns out to be really important because that sheath is grounded and the RF is applied to the needle. We did perform an experiment where we didn't include that sheath, and the problem with that was that without having a nearby grounding source, we were not able to, we could trap an ion, but the amount of electric field fluctuations that increased the micromotion was prohibitive to actually doing an experiment. However, with a nearby ground, we really limited those like long-term voltage fluctuations. And so these are mounted, this apparatus right here is mounted on a linear positioner that can be moved back and forth to vary this distance from the ion to the needle tip. In addition, a liquid nitrogen line comes in to this and is like a cold finger that can cool this needle down to about 150 Kelvin. And we estimate that to be 150 Kelvin rather than 77 Kelvin because of the thermal resistivity between where the actual liquid nitrogen line is and where the needle is. And here's a circuit diagram of the components of this. We have a cavity resonator that we use to apply the voltage, and we have some filtering circuits behind it in order to apply DC offset voltages. And those come down to the needles right here. To measure the temperature of the ion, we use something called Raman sideband thermometry. And this is just a basic schematic of how that works. If you have the ion in one of say your upstate, and you apply 2 Raman laser beams, you're able to transition it down to a lower motional state while also moving to the other qubit. So the transition rate the transition rate between these two is described by these equations right here, and you can see that if you apply a Raman transition to let's say you're in the n equals 0.1 state, and you try to apply your Raman transition to that, the transition rate will be much lower than if you apply, okay, let me restate that. So if you're in the n equals 0.1 state and you apply at the, so n equals 0.1, these states can be described as a probability distribution where just a thermal probability distribution. So let's say n equals 0. Let's say what is the probability of transitioning to below n equals 0? Well, that's 0 because there's nothing below n equals 0. However, if you apply a Raman beams and try to pump it up to the n equals 1 state, then there is actually a Raman transition rate. And you can see the asymmetry between these two transition rates by doing a frequency scan. And this is data from when the ion is in a higher motional state, and you do that frequency scan. And this is data from when the ion is cooled down to near its ground state, and you perform that frequency scan. So you can see that the only transition actually occurs when you try to increase its motional level by 1. And when you try to pump it down to below the n equals 0 level, there's no transition strength. So for this, let's see, this one would be, it's certainly within the Lamb-Dickey limit for when n is small. This uses the co-propagating laser beams. I'll describe in a little while that when we actually did the gallium arsenide trap and we used the same, actually they aren't co-propagating laser beams, they're at 9 so when we did these heating measurements, what we'll do is we'll cool down to near the ground state, and then let the system evolve for, well, not really evolve, but we'll let the system get heated up for a certain period of time, measure the heating rate after that period of time, and then repeat the experiment for longer delay times. And so in that way we can measure the heating rate between the ion as near its trapped minimum. And by then changing the ion electrode spacing Z naught, which I showed earlier, we get this data set up here. And that follows the line where the spectral density of electric field noise is proportional to e to the minus 3.5, which compares favorably to the historical data that we saw before, where there's roughly a e to the minus 4 variance. Another interesting thing in this experiment was when we cooled the electrodes down to 150 Kelvin, the heating rate dropped by over an order of magnitude for these points, for at least these two. So that told us that this half potential process could be thermally driven, and so that's one of the things that we want to experiment with in future experiments in this process. And so we're building another needle trap, and this one is actually made out of molybdenum. In addition, it will have ovens on the actual electrodes, so that instead of being able to take just 2 temperature data points, we hope to be able to take multiple ones, measuring the temperature using a thermocouple that's nearby. So, and to get to your question of, this is just a graph showing where that needle lines up with all this historical data. These big light blue dots are needle trap data points. And then to get back to your question about how does the spectral density of electric field noise relate to the secular frequency of the ion, these are some data points for that. And the way we took that was we moved the needles out, but maintained, and then we changed the secular frequency by increasing the static voltages applied to it. And so you can see that has about a 1/f